questions in the back? Can you hear me? No? Yes? Okay. So anytime if you cannot hear me, just raise your hand. Let me know. So in the last class, I talked about like the topic of the semester in general. We learned the bar element, we learned the bin element, we learned the 2D like CST, AST, Q4, Q8. So the basic idea is that, well, for real life structure, for example, this table or anything you are building or you are designing your senior design class, we cannot really solve it using our basic model, like from mechanics to a single bar, a single shaft, or a single bin to solve the problem. So what we need to do is that we need to discretize a complicated real-life structure into small elements. And for each element, we can use what we learn from mechanics materials to solve those problems. And in our FEA, basically, we have for each element, we have the element matrix equation. And for a big structure, we then assemble each matrix equation to a big matrix equation and solve the matrix equation. So again, for each topic, for like truss, bar, spring element, and bin element, and for CST, LST, Q4, Q8, we'll talk about what is the stiff matrix for each type of element. And then for the rest part, it's purely just calculation, like solving the matrix equation. So what happened in my previous class is that students, after my lecture, they could understand how to write an element matrix equation, how to do the assembly to assemble into a big matrix equation, but they don't know how to solve it. So basically, let's say you probably already learned, let's say simple situation, you have Coulomb on this end to apply tension, you have the K times X equal to F. Now we become a big matrix, K matrix times vector displacement. We have, let's say we have 1,000 nodes, and each node have 6 degree of freedom, so it's a vector of 6,000 vector and equal to the force, right? The force in general term can be a force term in X, Y, Z, can be a couple term. Moment in rotation X, Y, Z. So let's say in Abacus capability, you can solve up to 1,000 nodes for free edition, student edition. Then it becomes the maximum you can solve is 6,000 by 6,000 matrix, K matrix times a vector displacement vector, which is a vector has 6,000 components and equal to force vector, which is also 6,000. So that's the general idea. And of course, I'm not going to ask you to do that in your exam or anything or in your homework. That's why we need Abacus to do those. But in your homework, in your exam, we're going to test you if you truly understand those situations by solving 2 by 2 or 3 by 3. So still, you need to know how those matrix vector operation works. So the first class is the mathematical preliminaries. I'm pretty sure you guys learned it from some previous class or before you came to UF. So if this topic is very easy for you, just relax. We'll get more complicated stuff from next class. So this is just a review. We start from a vector. So, of course, it's a collection of scalars. We use a very simple situation of vector A, for example. It has 3 components. Let's assume it has 3 components, A1, A2, A3. And let's put definition, a collection of scalar. So by default, if you read the FEA textbook, all the vectors, well, vector can be row vector, can be column vector, but all the vectors in our FEA textbook, they are all column vectors. And sometimes when you might see like the right and the row vector and then put a transpose there because they just want to save some space for writing textbook. But all the vectors, they are column vector. And also you can imagine that when you have the big matrix K times X or Q vector equal to force vector, all of them are column vector. It makes sense. So just want you to understand that why sometimes they always have a transpose there. So by default in FEA, we always assume it's a column vector. And of course, this vector, if you have three components, we can also represent it can be a vector in three space, and we can write it in a way that instead of A1, A2, A3, we can write as this vector equal to A1 as the magnitude or length in the I direction. IJK, they are the unit vector in the X, Y, Z coordinate. A2, J, unit vector in the Y direction, plus A3, unit vector in the Z direction. So if A is a vector in three space. And of course, you probably already learned in the statics, like sometimes you have structure, you have force applied in X, force applied in Y, force applied in Z. Or you have a force applied in the random direction in the three space. And when you put in the force vector K, Q equal to F, and then what you do is that what is the component in the X direction, what component in the Y direction, and what component in the Z direction, and then it becomes the vector. So from vector form to this IJK form, or from the IJK form to vector form, you should know what it means. So the IJK, they are the unit vector in X, Y, Z direction. And of course, A1, A2, A3 become the components in those three directions. So in FA, you do need to decompose the force in the random direction, decompose to the X, Y, and Z, put in the vector form to solve the problem. And of course, the magnitude of this vector is square root A1 square, A2 square plus A3 square. And that becomes the magnitude of a combined force, of course. Or we can also apply this to the displacement in three space. And of course, if this magnitude equal to 1, it becomes a unit vector. So this is the vector part, and let's talk about the vector operation. Before we do the vector operation, we need to make sure that they are the same dimension. You cannot have vector of two components with a vector of three components and try to add these two vectors. It cannot be done. It has to be n vector, vector with n components and not a vector with n components. Then you can do the operation. So it has to be same dimension. And for addition and subtraction, of course, is the corresponding components. addition and subtraction and get a new vector. So let's say if you have a new vector equal to, assuming that A vector and B vector have the same dimension, then the components in the new vector equal to, let's use I, equal to the corresponding components in A and B. So this is addition and subtraction. For the multiplication, there are two types. Hope you guys remember. One is the vector product, one is scalar product. So let's start from the scalar product. I think it's very easy to tell the difference. I mean, scalar product, you get a scalar in the end. Vector product, you get a vector in the end. So the result of scalar product should be a scalar. So let's still assume the similar situation. Each vector has three components: A1, A2, A3. And B vector with the same dimension, three components: B1, B2, B3. So now the scalar product of A vector and B vector becomes A1, B1 plus A2, B2 plus A3, B3. And of course, we know that since it's in the end it's a scalar, we can also write this one as transpose times B or B transpose times A. And I want to say that, well, this is just like help you to understanding the basic vector operation. You can use MATLAB in your homework when the dimension get higher than 3 by 3. So in MATLAB, you can simply use as a prime is the transpose in MATLAB. This is a scalar product in MATLAB. So if A and B vector, they are the geometric vector in 3D space, then the scalar product A and B equal to the magnitude of A times magnitude of B times cosine theta. And theta is the angle between these two vectors. So this is the scalar product part. Now let's talk about the vector product. Actually, this is commonly used in your statics and mechanics materials for the vector product. The result should be a vector. And let's still assume that we have A and B with three components. Then the vector product, it becomes let's say unit vector in the x, y, and z direction, ijk. And the way we calculate is 2a3 b1 b2 b3. So the new vector is a2 b3 minus a3 b2, I vector minus a1 b3 a3 b1, j vector plus a1 b2 a2 b1, k vector. And of course, there's some way to help you understand and make less mistake. So basically, in the x direction, it is this one times this one minus this one times this one, right? And of course, the second term, there's a negative sign. And again, a1 b3 a3 minus a3 b1. And the last term becomes positive again and becomes a1 b2 a2 b1. So this is a vector product. And again, let's check if A, B are geometric vectors in 3D space. So all the difference, then the scalar product. Now this one equal to since vector product you get a vector, so there's a unit vector I put as n. You can use right-hand rule to find the direction of the unit vector, and the magnitude equal to magnitude A times B times sine theta. It's not cosine, so don't get confused of these two definitions. A magnitude, B magnitude, and sine theta times unit vector n. And of course, theta is still the angle between these two vectors. So for defining the unit vector, let's do a simple illustration here. Let's say we have A vector, we have the B vector, and use the right-hand rule, we know that unit normal vector should be in this direction. Now, let's assume that this is a, well, let's put this one as a unit normal vector. It represents direction of A vector product B, and the magnitude is 1. The length of this vector is A times A magnitude times B magnitude times sine theta. And since we know that, let's put this one as A, B. What if we have vector A times vector A? What do we get? 0. 0 vector, right? It's still a vector, but it's 0 vector. Is A times B equal to B times A? No. Which part is different? It's direction, right? Because right-hand rule, let's say A times B, you know that unit vector is upward, but if I have B times A, even though the magnitude of this new vector is the same, but it should be this direction. So just want you guys to understand that there are some difference of vector product and scalar product. So A times A, the vector product of A vector, if two same vector, we get the 0 vector. So basically it's a vector with 3 0 in it. If A has 3 components, B has 3 components, right? And B vector product A equal to negative A B, because unit vector direction, they're opposite. So this is a definition, vector and the operation of vectors, and just make sure you guys understand that there's a little difference between the scalar product and the vector product. The next one is matrix. And of course, a vector is a collection of scalar, matrix is a collection of vector. So let's define a vector has n by k dimension. Let's say for the first row, we have 1, 1, 1, 2, 1, and the first column I can write as 2, 1. I use n1, and the index here should become the first index is, let's put as n, and this first it represents the row index, and the second index I put as k. So the second index is a column index. The definition of this matrix, of course, is n by k. Definition here. It is a collection of vectors. So this is a n by k matrix. And of course, a special situation when n equal to k, it becomes a square matrix. And in this method, we will see that for all our FEA problem, before we apply boundary condition, all matrix in our FEA before apply boundary condition, they are square matrix. So n and k, they're all the same. It becomes square matrix. And there are some small concepts I want to talk about for the matrix. The first one is transpose. And of course, it's just switch rows and columns. So I just use a simple example here. Let's assume that we have a matrix 1, 2, 3, six components, and then transpose. We just switch the rows and columns. It becomes 1, 2, 3. Now this is how we do transpose. And of course, when the matrix dimension get bigger, you do not need to do all the calculation by yourself. You can use MATLAB. It will automatically do the transpose for you. The second concept is a symmetric matrix. Again, this is a very important concept for FEA again. So because you will later see that all our matrix is not just square, it's also symmetric. We will explain later, but before we apply boundary condition, all the matrix in our FEA, there are square matrix and symmetric matrix. So basically is A equal to A transpose. Let's just write a very simple example here. Let's assume that if we have a 3 by 3 matrix and we have 2, 3, 4, 5, 6, then this symmetric matrix is symmetric about this diagonal term. So the rest component should be 5 here, 3 here, 2 here, and is equal to A transpose. And again, symmetric matrix is a special case for square matrix, and we have a special case for symmetric matrix, that is the diagonal matrix. And I'm pretty sure that you guys used diagonal matrix in mechanics materials or aerostructure or Mech 1 before. Are you guys familiar with like some concept related to the diagonal matrix? What is that? Yes, that is diagonal matrix, but if let's say you learn something in the solid mechanics, we use diagonal matrix. What are the stress components? Principal stresses. Remember? So let's say you have a structure, you have torsion, you have tension compression, you have bending, you have transverse shear, and you use all of those calculate stress components 3 by 3. You have sigma x, sigma y, sigma zz, tau x, y, tau, and all the shear stress components, all the normal stress components. And now let's say I want to decide if the structure will fail or not. So if our material is a brittle material and it compare with the maximum normal stress of the material strength, what do we need to find out? That for this state matrix in the global coordinate XYZ coordinates, we need to find the principal stresses, which means that for those 3 by 3 matrix, we need to calculate the eigenvalue, and it becomes all shear stress becomes 0, only the normal stress stays, and we compare the maximum normal stress or maximum principal stress with allowable strength of the material, and we decide, okay, it will fail or not, right? So we do used these things in our previous classes before. So all of diagonal components become 0, or in solid mechanics, you can say that all the shear stress component becomes 0, only normal stress is sustained. And those diagonal terms become the principal stresses. So put a simple example here. If for a 3 by 3 matrix, now all the rest part becomes 0. And of course, again, when you need to use MATLAB, you do not need to really define like all those type, the whole n by n matrix, and have all those 0 terms defined here. What you can do is that you just define a vector. Let's say, let's use a different color. In MATLAB, you can define a vector. Let's use this one for example, 1, 4, 6, and then you can use diagonal A, and MATLAB will generate a n by n diagonal matrix for you. Instead, you need to type all the zeros, wasting your time. And now, especially the diagonal matrix is now all this diagonal term becomes one. It is called identity matrix. So identity matrix is also very important. Well, it's function as one. Let's say in the scalar operation, you have something times one equal to that still that number. In matrix operation, you cannot really say that I have matrix I times one equal to that matrix. No, you need to have a matrix times a identity matrix which function as one and then equal to the other matrix. So so it's basically a special case of the diagonal matrix. Now all the diagonal term becomes one. Let's say if it's a 3 by 3 matrix, I use identity matrix, I use 3 here, then it's basically 1, 1, 1. Other components become 0. And in math, of course, you don't need to type all those things. You just use I, n. N means, let's say if you have n by n matrix, n means that n. So let's say if you use 3, it will MATLAB will generate this one for you. And if you use 1000, they will generate a 1000 by 1000 identity matrix for you. And of course, as I said, in the matrix operation, it functions as one. Or we can say that I times A equal to A times I equal to A. The dimension is the same, of course. The next one is calculate determinant of a matrix. I will only talk about the 2 by 2 and 3 by 3, and I only expect you to know how to calculate 2 by 2 and 3 by 3 in your homework. In exam, I only expect you to calculate. Well, I can ask you 2 by 2 and 3 by 3 in the exam also. Anything higher than that, MATLAB. So for 2 by 2, let's say we have a matrix with 4 components, 1, 1, 1, 2, 2, 1, 2, 2. Then the determinant of this one equal to 1, 1, 2, 2 minus 1, 2, A, 2, 1. And of course, determinant is a transition step when we need to calculate inverse matrix, because you need to know that we have, let's back to FEA. We have the K matrix, Stiff matrix for the structure. We have the degree of freedom you need to solve. We have the force applied vector K times Q equal to F. So what do we need to do in FA that we need to solve for the Q vector? So it's inverse of the K equal to times the force vector. Well, we normally assume that you know the structure, you know the K matrix, you know the force applied, you know the force vector. The thing you need to solve is a Q vector, which is the degree of freedom or displacement or rotation or anything, degree of freedom. So what you need to do is that you need to calculate inverse of A times the force vector. You get a Q, right? And to calculate inverse, you need to know the determinant. So this is like more a intermediate step you need to use for solving our FEA problem. 3 by 3, let's assume we have 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 3. Again, the result becomes this one times 2, 2, 3, 3 minus 2, 3, 3, 2. And the same thing, add the negative sign for this term, and we repeat it for the 3 terms. Let me write quickly here. The first term, A11, 2, 2, 3, 3, 2, 1, 3, 3 minus 2, 3, A, 3, 1. And the third term becomes positive again, 1, 3, and we have 2, 1, 2, 2. Oh, there's something wrong. No. This one times this one, 3, 2. And 2, 2, 3, 1. Let me double check. 2, 3, 3, 2 minus 2, 1, 3, 3, 2, 3, 3, 1. 2, 1, 3, 2, 2, 2, 3. Yes, this somehow. Okay, yeah, this is the correct form. Of course, you don't need to memorize anything. If I need to solve 3 by 3, I mean, after apply boundary condition, I need to solve the 3 by 3 matrix equation. I will provide this one. You don't need to memorize anything. And of course, if the determinant of any matrix equal to 0, the matrix is singular. Again, trying to make some connection with this part, with our FEA part. All the distribution matrix in our FEA before apply boundary condition, they are singular matrix. You cannot solve them. You don't need to understand this part now. We'll explain in detail later. The next one is eigenvalues. Oh, so for anything, let's talk about the inverse. I forgot the inverse part. Let's talk about inverse of matrix first. So determinant, I would expect to do for 2 by 2 and 3 by 3. Higher than this, you can use MATLAB. And for MATLAB part, you can use DETA. Of course, you define the A matrix first and use DETA. They will give you the determinant. For inverse matrix, I only expect you to calculate 2 by 2 in your exam. In homework, I can do higher dimension for the matrix, but you can use MATLAB. Let's assume that we have a 2 by 2 matrix, A matrix, 1, 1, 1, 2, 2, 1, 2, 2. Inverse, it's equal to 1 of a determinant of the matrix. And of course, since it's 1 over the determinant, we know that determinant cannot be 0. It cannot be a singular matrix to calculate inverse. Determinant should be non-zero first. The diagonal term, we need to switch the position. And off that term, we need to add a negative sign. So this is how to calculate the inverse of 2 by 2. For anything higher than 2 by 2 in MATLAB, you just use INV. Define a matrix inverse A. They will give you the inverse of matrix. So let's put it here clearly. If the determinant equal to 0, there's no inverse. And in our FEA, we talk about later that since our matrix before by applied boundary condition, they are determined they are 0. We talk about later like how to remove the singularity of the matrix and actually solve the Q vector. And of course, if a matrix is invariable, we have let's assume that B matrix is the inverse of the A, then this one equal to I don't know. I didn't do anything, I promise. Connection failed. Oh, my Wi-Fi. You know what? Oh, okay, okay. There's no Wi-Fi. iPad cannot. This one works. This one has Wi-Fi. This one does not need Wi-Fi. That's why my iPad is not. I don't know. Is it back? Is the Wi-Fi back? Let me know. Seven minutes left. I think we can continue on Wednesday. Sorry about that. I don't know what happened.